Hello, everyone. I'm down in Australia, but time is good here, and I'll see if I get my go. So, yeah, in the distant future, when there's a large number of people on Mars, I believe that there's going to be a time when they want a Earth-like gravity environment. So I've been toying around with a program called OpenSCAD and Blender and produced a description of how that might work. I've done this as a hard science fiction concept, and the idea is to make it as realistic as possible using materials like steel and remaining within the parameters of those materials and adapting the design to work on Mars. So let me bring up a picture. So the idea is this particular centrifuge is to produce Earth gravity.
I hate to interrupt you, but your screen isn't being shared.
Oh, okay. Got it. That's better.
Perfect.
I hope. Right.
Perfect.
So this is the first slide. I wanted to give an idea to people of how large a facility this would need to be. So with a small centrifuge, you basically have to stay in one place because the curvature of the acceleration as you move about is quite significant. So a small centrifuge can't have large open spaces, but a small centrifuge is still fine if you just want to be able to sleep or sit at a desk. So I thought initially on Mars, a small colony might have a small centrifuge, which is inside a building, much like the ones NASA use for their training. They might be bigger than that, but generally you can't move around much, and there are significant distortions in the way the gravity works. So the next step up from that, I should go back actually. When the settlers first arrived, they may actually be in a very small spacecraft, or actually it's quite large, a starship, similar to what Elon Musk is envisaging. In a craft that size, you can have a running track where people would run around the track. And if you sprinted fast enough, you would actually generate a centrifugal force equal to Earth's gravity. So that would always be available to anyone on Mars who arrives on the surface. In future, they would go to the next size torus, or this facility here, and then they might build something bigger. And for scale here, I've got a picture of the Great Pyramid of Giza. So it is a significant amount of materials and effort to build something this big, but if you're aiming to have a city of 100,000 people or something, this scale of building becomes feasible. So here's an example of a 100-meter centrifuge. And in a centrifuge that size, you could probably have small rooms about the size of sort of a lounge room in a house, and you could walk around in that, and it would appear to be relatively flat. But for every 2 steps you take in a centrifuge that small, the angle of the floor will change by about 1 degree. So there is a very noticeable curve in it, but it is still, you're able to walk around and probably jog and even play sports like table tennis or squash, which don't require a large area. But for sports which we're used to on Earth, like tennis, for example, or football or basketball, you actually want a playing field probably about 40 meters by 20 meters. So that's where you need a large centrifuge the size of what I'm going to be describing. Now, I think what I'll do next is I'll bring up the video I made. So this little guy here, can you guys see that? I hope so. But he's supposed to be about the size of a 1.8 meter tall fellow, and behind him is a starship. And I'll play the video, and this gives a run over. So we zoom out. There's the foundation of the centrifuge. It's got a center hub and an outside running track. There's some motors, which are kind of like train motors. Then there arrives the outer hull of the torus and the central hub and an access bridge. The access bridge is in part supported by suspension cables. Inside the torus, I've hidden the outside hull for now. frames, and in those frames, we have large sectors which are able to rotate so that as the torus speeds up, they can tilt so that people always are standing on a flat surface. Now, this thing is absolutely enormous, about 250,000 tons, but it gradually speeds up. And as you see here in the video, it's slowly speeding up. In reality, this would probably take over an hour to reach full speed. And we'll show you how it works down here. So underneath, we've got a train track style system, and this area under here, which is actually going to be pressurized at about 15% of Earth's atmospheric pressure. And that helps support the enormous weight of this torus as it spins. So it's kind of like a hover train or a hovercraft. Then in the central hub here, we'll walk along the ground here, and you can go up a ramp. And at the center of the hub, even though the outside is going to be spinning at about 230 kilometers an hour, the center hub is only doing about 20 kilometers at the point where we enter it. So you can basically jump over that and get into the moving part of the system. Then we can go up here to these access arms. There would be airlocks and so on in this system, of course. I don't show these in the video. But we travel down to the center, down the access arms, and then inside the torus, we have the sector pods, which are at this point where we're doing 230 kilometers an hour, tilted at an angle of 70 degrees. And here's one of our stadium type areas. We've got a tennis court in this one here. So the tennis court, the outside lines, the size of a full stadium tournament court. So that's actually similar in size to what you'd use for indoor soccer or basketball or some other indoor sports. So this is a good size for the inhabitants of Mars to have an Earth-like area where they can play the kind of sports that you would play on Earth. Now, back to the presentation slides. The reason the pods have to tilt at 70 degrees is when you add Mars gravity and the centrifugal force from the 3.7 meters a second of Mars gravity together, you get an angle of 70 degrees, and at that angle you get Earth-like gravity. So no matter what size centrifuge you use on Mars, if you want to reach Earth-like gravity, you will always be tilted at 70 degrees. Even for a small running track, it will always be 70 degrees. Just an interesting bit of trivia there. The torus I'm showing in the video is about 880 meters diameter, and it has a small diameter, which is the circumference of the section of 64 meters. That allows you to have fairly large buildings, about the size of a 10-story building inside. Now, I'll go over some of the sort of activities that might be possible in the different sizes. So at the 25 meters, you probably can only do stationary things. That would kind of be like sitting in a small room and not be able to move around much, and getting in and out would be quite easy. You could stop and start a small centrifuge quite easily. At the 100-meter diameter radius, you get to the point where if you had that size centrifuge indoors, it's doing over 100 kilometers an hour. And so you get a tremendous amount of air drag at that speed. And you actually have to build your centrifuge completely outdoors, because although Mars has a thin atmosphere, it still produces a significant amount of aerodynamic drag. So at that point, you actually have to have the surface, the torus, completely outdoors. And as you saw in the pictures here, you have an indoor torus. Outdoors, you don't have to contend with as much aerodynamic drag. Quality of the gravity. So even though this is a very large torus, people will still notice there are some effects. So there will be a need to have a slightly curved playing deck, which won't be a huge amount of curve across the distance of the playing floor. Would be about 2 degrees for a tennis court. From end to end, the lengthways, it would be much less because of the way the centrifuge works and the angle of the floor. It's not a huge amount. The Coriolis force and the Avotus force have an effect when you're moving about. When you run in the direction that the torus is going, you would get around about 5 to 10% heavier if you sprinted really fast. In a smaller torus, that kind of effect becomes very significant. In a really small torus, you could actually run so fast that you would basically become bound only by Mars gravity, and you would fall sideways across the floor if you tried to run too fast, because you would only be affected by Mars gravity, and the torus sloped at 70 degrees, or the playing deck you would be on at 70 degrees, you would basically slide straight off the floor. So a large torus minimizes that effect, and so you can play quite easily. This would allow sports where you can slide around and stop and start very quickly. The high gravity of Earth has the benefits that it gives you a tremendous amount of traction. When a car wants to take a corner or a tennis player wants to stop and change direction, having a high gravity allows you to get a lot of traction on the ground and just stop, change directions. Under normal Mars gravity, that won't be possible. So that's actually one of the reasons why having a torus like this is really good for exercise, because it means that people will remain adapted to Earth-like gravity, and there are benefits in that. Let me see if I can find some of those. Gone through that. Going to some of the structural forces involved in building this thing. So I didn't want to make it out of unobtainium or anything like that. To give an idea of what's involved in the strength of this thing, the air pressure inside is trying to stretch the entire structure out. So that actually produces, it's like trying to rip this thing apart with a force of around about 44 kilotons. That's basically like trying to lift 44,000 cars off a piece of rope. So the structure of the torus has to be very strong to withstand that. And then because it's rotating, you can double that force. We add another 76, another 44 kilotons roughly for that as well. And you get a combined force from the air pressure and the centrifugal force equivalent to about 50,000 large motor vehicles. So for that reason, the hull of the torus has to be made out of very strong material, around about 35 millimeter thick steel, to make it strong enough to withstand atmospheric pressure. And from that, you can work out the kind of mass you need and the structural integrity. So it does require a lot of investment. It is difficult to make, but those kinds of materials are actually quite common for large structures on Earth, like bridges and things. So as I see it, the kind of materials that I'm talking about here are readily available. I can go down to my local hardware store and actually buy a slab of 35 millimeter thick steel if I want. It's not cheap, but it's readily available. So this is not a design which is unobtainable or impossible to make if you have sufficient resource available. So the suspension system, we have to deal with all those forces, and in operation from the air pressure, it will actually stretch out the torus so that its radius changes by around about 20 centimeters. And then on top of that, you've got thermal expansion and contraction, and that can actually change the radius by another 43 centimeters. So we're talking quite large distances. So in the design, the motor drive systems would actually have to move left and right during operation under control of a computer system, which measures the expansion and contraction and tracks the torus tracks so that it doesn't derail during operation. So there are significant design effort that has to go into the way everything works. the entire track of the torus also has to be able to do those same expansion pressures. The inside temperature of the torus is going to be about 20 degrees during operation, but Mars normal temperatures vary from 20 down to -70 around the equator. So you do need to take account of these things in a proper engineered design. So yeah, it's not straightforward, some of the problems you have to solve. Also, the air pressure inside, that helps support the weight. Now, the wheel system is great, but you do get rolling resistance and wear and tear on the bearings. The kind of weight I envisaged was actually similar to the kind of load-bearing capacity that you see in heavy freight trains. So it's not unreasonable that you could support the entire weight just using the wheels and the traction system. But by using air pressure, you can support far more weight and take most of the load off the wheel system. So it makes it a lot easier, and you reduce your energy use from this thing. The energy used to actually drive it just to overcome some of the rolling resistance and the atmospheric drag from the access arms. We're talking well over 10 megawatts, somewhere around 10 to 20 megawatts to actually drive this system. So it's a substantial amount of power, but that's just quite a relatively small solar farm these days, is 10 megawatts on Earth. So it's not unreasonable to expect a Martian civilization to develop something like this. As I said earlier, total weight of this thing, probably 250,000 tons. To travel down the arms and so on, you would gradually be tilted more and more as you travel down it. So you would have pods similar to what you might see on the London wheel, where as it goes around, the pods tilt to always keep the people inside up the right way. So you would probably have something like that to travel up and down the arms of the torus as people enter and leave. And the connection where these join to the torus has to deal with a whole bunch of problems like the expansion and contraction. So I didn't actually get into the design of those yet, but there will be ways to deal with that. And the center hub uses a similar suspension system to the outside ring of the torus. So it has access doors, which you saw in the video. We can just enter through there for an airlock and go down the arms. And there was also the idea that you could... Oh, we're getting near the end, are we?
Yes, you have 5 more minutes.
Oh, okay, cool. So you could also enter this thing through a pressurized tunnel system. So people could go from one part of a colony to another that way without having to wear a spacesuit. The entire thing, of course, would be pressurized. Thermal considerations, the outer hull. This is going to be a common construction technique to basically every building on Mars. You would have acoustic damping on the inside layer, but so it doesn't echo around like a concert hall. You have a pressure hull around about, for a non-torus centrifuge of 60 meters diameter, it would be about 17 to 20 millimeters thick. Because we have to deal with all these extra forces, it's about 35 millimeters thick. Then you would probably have some radiation tile cladding using high hydrogen type materials like plastics or hydrated minerals. Then you have a thermal insulation barrier like rock wool. And then you have an outer cladding layer, which provides a aeroshell and just a physical protection barrier to the buildings. And most buildings on Mars and vehicles will use a similar construction technique. Thermal insulation is surprisingly effective on Mars. Because of the thin atmosphere, it does make thermal insulation much more effective. You can get an R value of over 30 quite easily, and probably a lot higher if you use more exotic techniques. This shows how people would get into the tilting sectors. They would have a shaft down to the bottom deck. People want to get in and out, they can just go to the bottom here, go in the shaft and go to any floor they want. And this people would probably not be in this all the time. They'd be leaving and going as they want. The energy needs per person are actually quite meager. They're similar to a house on Earth. So it's not ridiculous to expect to be able to provide energy for this. The design cost in terms of the energy required to make the materials to build it would require a 1 gigawatt nuclear reactor to operate for about 5 months to produce all the steel required to build this thing. So it's kind of like something that you could envisage building on Earth for a moderately sized city in a relatively short amount of times. I would imagine it would probably take 5 years and a population of about 100,000 people to build something like this. And you might have several of these in a large city. So compared to O'Neill cylinders, which I'm sure some people would have heard of, this is relatively more obtainable. I would consider an O'Neill cylinder to be almost a fantasy design. The outer hull on an O'Neill cylinder, for example, as he envisaged, requires a thickness of steel of several meters thick, whereas what I'm talking about is only 35 millimeters thick. So the design I'm showing here is obtainable and something that I actually believe the Martians in a future, maybe 50 years from now, would actually build these kind of things. So I wanted to provide a visualization of that, and that was why I made the video, to get a feel of how it would look and feel. And that video is available on YouTube. If you Google Stephen Humble and look for toroidal gravity facility on Mars, you'll be able to find that. I'll be doing an enhanced version with sound of that in the near future for people to have a look at, and probably add an enhanced version. But for now, I've got the basic version you saw with some subtitles there. If people want to ask me some questions, I can explain a lot more about it if you need to.
Thank you so much, Stephen. I do have a couple questions. Let me find the first one here. This is from Douglas, and he would like to know, how would people, cargo, enter, exit the complex once the centrifuge has already been started in rotation?
That's a good question. So as you saw in the video, because the outside's going 230 kilometers an hour, you can't directly enter that part there without a great deal of difficulty. So the center hub, because that's at the center at that particular radius, it's only doing 20 kilometers an hour. So let me go back to the video here where I've got a, so as you see here, you can walk up a ramp and onto this platform. And even though the outside's going really fast, at the point where you cross the barrier from this non-moving section to the moving section is only 20 kilometers an hour. This doorway you see here is 5 meters high. So you could have a truck deliver a shipping container, drive through there, and the area here before you cross the doorway could in theory be a moving deck. So you could drive up on here. This deck here could start moving to match the speed of the door, which is only 20 kilometers an hour when you cross this point. So you could go in here, close this door here, which is going to be an airlock in the real thing. And then you're inside the moving section, and you would take an elevator or a stairwell, which is not shown here. This is a very basic model of the design. And this is where you would get into a pod. You would have pods which recirculate, kind of like a travelator or an escalator system. And as you move down here, you would be accelerated to the full 230 kilometers an hour. And at that point, as you move down, you're now in an Earth-like gravity environment, and you would be tilted at the 70 degrees. So you actually, in operation, these pods are tilted at 70 degrees, but because you're you've got Mars gravity and the centrifugal force. To a person standing on the deck playing tennis or basketball or whatever, they're going to be upright. So that's how you get into the torus, through that system. And it's actually relatively small. You could actually walk in there through those doors with a spacesuit on, or come through a subway system through the center shaft, which you saw just here. This shaft here would allow you to come through a subway system up that shaft and do the same thing. So there's a couple of ways you can bring goods and services into the torus through those things. So I hope that explained it well enough.
Thank you, Stephen. We do have we have a couple minutes to answer one more question. And this question is from Peyton. He said that he heard that you used Blender to create this project. What are the advantages of Blender in modeling large-scale projects like this? And is it possible, or maybe a good idea, to use CAD programs more suited toward product design, such as Fusion 360, the app that Peyton uses most?
I actually didn't just use Blender. I used Blender to create the visualization. The primary program I used was a program called OpenSCAD, and that's a parametric design tool. I'll just quickly bring up a window of that. I hope you guys can see this. So this is the modeling tool I use, and I create all my models using a parametric design, and that allows me to change sizes, and it's a solid geometry engine, and you can actually take these models and print them out. I've created a few things and printed them on a 3D printer, and this allows you to create very precise designs. Everything here is measured to the whatever degree of precision you want. So this particular image here is one of the pods, for example. This is an outer bearing on which the sectors would rotate. There's an elevator shaft in the full design. This elevator shaft here reaches to the bottom of the torus. I can go back to another window I've got open. That would be how you look through there. So there's that elevator shaft. So what I do is I take my SCAD models, I import them as STLs into Blender. Then in Blender, I create the surface coloration, the texturing, to create that nice three-dimensional visualization animation you saw. So I do actually use a CAD program. Blender, as you notice, is probably not the right tool if you want to create a precision design. So I kind of use two different tools for that. I hope that explained it.
Well, we are out of time, Stephen. Thank you very much. Peyton actually made a comment too. Thank you very much. I think he really enjoyed what you just showed him, because I got an immediate thank you in the comment section. Thank you very much for your presentation. It was great. And we're going to go ahead and conclude this session.